Hi, I'm Brian Schwartz. I'm on the electrical design team. I've been working on testing and reliability to make sure the drone works properly for the competition.
Hi, I'm William. I'm the lead software designer of the club, and I manage the ground control station.
I'm Jonathan Wynn on the mechanical design team. I design and 3D model the drone on Fusion 360, Inventor, and AutoCAD.
Hi, my name is Braden Wolf. I am the electrical team lead and autopilot coordinator for the team. My job is to make sure the thing flies and doesn't crash, and there's a lot of code that goes into it, hence the food.
I'm Matt Minogue. This is my 4th year on the team, and my 2nd year as team captain. I've been proud to oversee a group of very talented guys building this massive octocopter, and we hope to have some success this year's mission demonstration. So these plates are made out of acrylic with a little cover on each side. Originally, the plan was to use carbon fiber. However, carbon fiber is expensive and difficult to obtain, especially if we have to get parts custom made, whereas these are, I think this was $10. So we can focus more of our budget to the electronics and the software portion. We don't have to worry about the hardware. In addition to using acrylic parts that are easily accessible, we 3D printed a lot of connecting pieces, such as the arm brackets and the motor brackets and the landing gear. 3D printing allowed us to make parts in-house, which meant that we could work on a faster time scale and lower budget. Again, that helps so that we can focus more money towards our electronics components, our software components. We don't have to worry about printing arm brackets or getting them custom made or any issues with manufacturing. We can do all of our parts manufacturing in-house.
This year the AeroCards attempted to build a secondary backup drone with 8 rotors instead of the previous 4. This was decided due to the increased flight time from dual batteries, the amount of torque the motors could provide, and for stable flying with backup options. If one rotor goes out, the other 7 can still balance the drone to make up for it. Quadcopters are less stable, provide for less room for batteries, and do not allow for backup options if motors go out during flight. We are using a cube flight controller with 8 isolated electronic speed controllers, 1 for each motor that is attached to the arms. Our previous drone used 4 electronic speed controllers and a Pixel Hawk flight controller. Our hopes are that the newer backup drone is complete by the competition. For now, that drone remains to be a backup. We have more testing complete with the quadcopter, yet the octocopter has proven to be quite stable as well. We hope to see some improvement in our missions this year, as well. Through MAV proxy, we have set up our drone to complete the stationary vehicle drop mission. We used Python as our coding language, and we also incorporate the use of sensors, global positioning systems, and other telemetry through man proxy to deliver smoother flight and more data to the ground control station.
So here we have 8 of the arms and the mostly completed body section of our octocopter.
And the 2 batteries we'll be using for.
As well as the 2 batteries in their respective cases. So each arm consists of a 3D printed motor bracket, the motor itself, as well as the wires, which are currently nice and organized, and a carbon fiber, thank you, Will, and a carbon fiber tube that is nice and rectangular so that there's no rotation. On our previous design, there were some issues with alignment between the motors and the respective motor plate. But we have our radios. We have 2 telemetry radios for redundancy. We also are going to have 2 GPS modules for redundancy, as well as possibly 2 power modules. So this thing should stay in the air even if one or more system fails.
During our test sequences, we simulated a virtual drone using our computer software. Through this we could tell if all of our electronics would be set up according to proper voltage and other electrical restrictions. During our physical tests, the propellers were removed from both drones to sequence a real flight with an on-the-ground autonomous demonstration. This limits the safety hazards and provides a better view to the team as to what does and does not work.
This is why this is why we're using bullet connectors.
Bullet connectors was one of the best decisions we made all year.
I can remove this guy.
Will and Braden took care of coding our sensors and imaging performance for each drone. While equipped with sensors, they are able to detect their surroundings to a degree and analyze them. Our members working on the ground control station also aid in the analysis of flight with drones this big. We like having backup plans for when things do not go as planned, so we always prepare for the unexpected. Our airdrop uses the same setup as last year. It performed very highly, and has since been improved to increase the chance of a successful drop. While the vehicle is still in production and development, the mechanism on the drone works cleanly. Our waypoint missions have resulted in great success from our tests as a direct result of team coordination and the sensors we use. This helps to give the drone a feel for where it is on a map to stay on track where we need it to be. Team coordination also helps greatly to make sure everyone is on the same page about the drone. As we have run through our code and tested our quadcopter several times this season, we are very confident in its abilities to score very highly on its own behalf from the work our members have put into coding and design. We have a large field to practice and run developmental testing on. This helps to improve coding accuracy and understand through learning experiences all about the drone.